Okay, welcome to third class of advanced environmental chemistry. Okay, in the last lecture, we learned how to build the half reactions and how to combine two half reactions to make a complete oxidation reduction reactions. Also, we listed the half reactions in the order of the Gibbs free energy, and we learned that the ones at top part is oxidant, and it appears at the top it has a high or strong, say, oxidizing power, as the Gibbs friend is pretty positive. So when you combine two half reactions, we combine the lower one minus the upper one. So we add this plus minus this. So the free energy will be negative. That means the reaction, the oxidation reaction, reduction reaction will proceed spontaneously or to the direction we wanted, from reactant to product side. Okay, now we're going to think of the biological reaction, oxidation reduction reaction. The biological oxidation reduction reaction is the all reaction that mediated by bacteria or the microorganisms. So why bacteria or the microorganisms do the oxidation reduction reaction? The main purpose, or the main single purpose of it, is to produce cells, so to grow, so bacteria to grow. So the only reason is they mediate the oxidation reduction reaction to grow. So then we'll look at this graph a little bit, these figures a little bit in detail. Say, what is the energy source for the bacterial growth? That is the electron donor. So mostly it's an organic compound, but as you see in this side, say hydrogen is a good electron donor. It can donate electrons. So electron, a compound that can donate electron, is the compound that gives energy, that provide energy to bacteria. Then, so we can assume that the electron itself is energy. So electron itself is energy. So if some compound is releasing electrons, is releasing energy. So how bacteria use these electrons? Say, to make our cells or to produce their daughter cells, they need energy to do work. So most of the energy contained in the electron donor is used to produce energy that makes cells. So to make energy, what they need is electron is transferred to the electron acceptors. That is oxidizing agent. So while transferring electron from donor to acceptor, the energy is released. And the microorganisms use this energy to produce cells. So if there is organic compound is available, they'll use organic materials to make cells. Or if organic material is not available, then they can reduce this carbon dioxide to organics, and then they make the building blocks. Then finally convert these building blocks into a cell. So the electrons, a part of electron is used for the production of energy, and part of the electron donor is used for the cell synthesis. So we can divide the electrons into two categories. The fraction that is used for energy generation, and the other is a fraction that is used for the cell synthesis. So that's why you have the Fe is a fraction that was used for the energy generation, and fraction of electrons that is used for synthesis. Then, we can imagine that the donor, about this donor, Fe electrons goes for the energy generation. So this needs, oxidizing agent, electron acceptor. Then it will produce energy, and this will use for this amount of electrons is used for the cell. So if we have this concept, then we can make the electron donor plus electron acceptor will go to the product, end product plus cell. So we'll practice this in the later class, later section. Okay, let's go back to the previous case. Here is some list of half reactions for the biological oxidation or reduction. Here we have glucose as electron donor, so that is organic. And this one, hydrogen, is inorganic compound. And this one is also this pretty good electron donor. Also, this acetate or methane can be an electron donor or electron acceptor, or this one can act as electron acceptor. Okay, let's make it simple first. We're going to compare the aerobic and the anaerobic process. So aerobic process is the process that utilizes oxygen as an electron acceptor. On the other hand, typical or strict anaerobic process is use carbon dioxide as electron acceptor. So if glucose is if glucose is an electron donor and oxygen is an electron acceptor, then we'll have to combine these two reactions, electron donor, electron acceptor, right? Then the free energy available from this reaction is about minus 41 minus 78 is about 120 kilojoule. That is the energy available from electron donor to electron acceptor reactions. That's for the aerobic. In the anaerobic case, usually carbon dioxide is electron acceptor, and the energy is about minus 41, minus 24 is minus 17 kilojoule. So for the same electron donor, if oxygen is used as electron acceptor, it's about 120 kilojoule is available. On the other hand, if carbon dioxide is electron acceptor and this carbon dioxide is reduced to methane, the energy available is only 17. So it's about say 15% or less than that is available for the aerobic case. So if we compare these two, aerobic and anaerobic process, which process will make more cells? So for the same amount of electron donor, aerobic case is 120 kilojoule is available, and the anaerobic case only 17. So which can grow faster? That's the aerobic case, right? So that's why the aerobic process is always faster than the anaerobic process. Okay. Then what is fermentation? So fermentation is a process that do not use external, say, electron acceptors. For example, say if glucose release electrons. Okay, I'll do it again. Okay, so if it okay, let's make it in this way. I will explain this. Okay, glucose is release electrons, and those electrons is captured by carbon dioxide or by carbonate and produce acetate. So that one is anaerobic process, and the energy is very small, minus 41, minus 27, that is about 14 kilojoule is available. So the energy available is quite close to the strict anaerobic case. But what fermentation really means is, say, this carbon dioxide is not a real electron acceptor. It's kind of, say, imaginary electron acceptors. So if we look at this, reactions, glucose fermentation into methane and carbon dioxide, say the average oxidation number of this carbon is 0, right? And the oxidation number of this carbon is minus 4, and this one is plus 4. So if he adds up the oxidation number of these two compounds is 0. So 0 to 0. So this is an oxidation reduction reaction, but there is no external electron acceptors. So the electron is redistributed in the compound. Okay, I think it's, this one is not a good example. Okay, let's do this. Acetate to methane to carbon dioxide. Say, repeat calculate the oxidation number of this carbon is going to be -3, and this one going to be +3. So without giving electron to the outside, one electron, if this carbon toss or transfer one electron to this carbon, then what will happen is this one gonna be +4 oxidation state, and this one would be -4. So if one electron goes, say hydrogen also goes, it's also going with the one electron. So the final product is methane, which has -4 oxidation state, and this carbon dioxide is +4 oxidation state. So the electron is just transferred from one carbon to the other, or one carbon to the other carbon. So it's not going to the other electron acceptors. So electron business is inside the original molecules. That is the fermentation. So this is a good example of fermentation, methane fermentation. Methane is produced by redistributing electron within a molecule. So in some sense, we usually tell us that the methane fermentation, but if, say, methane is produced in this case, then this one is electron donor, and this one is electron acceptor. So strictly speaking, this oxidation reduction reaction produces methane, but it's not a fermentation, right? So if there is a oxidation electron donor and electron acceptor, we say it's not a fermentation. It's kind of respiration. Okay, so I think I mentioned it clearly. So if there is an external oxidant or electron acceptor, we call that respiration. So for the respiration, we need the electron acceptor. And for the biological viewpoint, oxygen is a pretty good electron acceptor because they can produce more energy. Nitrate is also a good electron acceptor because the energy difference is not that big. It's about 10% difference. Sulfate may act as electron acceptor, but if you look at the Gibbs free energy, the energy released by using sulfate as electron acceptor is much smaller than these two cases. Or rather, the sulfate reduction is more or less close to the methane production. So it's about 23.5 and 20.8. So there is no big difference. But, however, this sulfate reduction, this is a respiration. The sulfate reduction produces a little bit more energy than this methane production case. So, if two species, sulfate reducers and methane producers, are competing, say, for the electrons released from the organics. So if this one is electron donor, and if we combine this with this reaction, that is a methane production. If we combine these two reactions is sulfate reduction, which bacteria will dominate or grow fast? This one is the one that wins the race. So sulfate reducers is always, say, dominant to the methane producer. So that's why, say, sulfate reduction proceed first, and then after sulfate reduction, methane production occurs in the anaerobic reactors. Okay, as I told you before, say, oxygen is the best electron acceptor. Then the nitrogen is quite equivalent to oxygen, and sulfate is here. So sulfate is a little bit worse, but not a good electron acceptor than the upper two. And sulfur, elemental sulfur thiosulfate is somewhere around here. One interesting thing is Fe3 is a pretty good electron acceptor, quite compared to the oxygen. So Fe2 equals Fe2 plus, or the nitrate 2 and 2. Also, this nitrate is pretty good electron acceptor, although this nitrite is not a common compound in the environment. Okay, let's go to this next slide. So, to complete the biological reaction, as I told you, say, electrons from donor, so half reaction for the electron donor. So part of this electron goes to the cell, and part of it goes to electron acceptor. So if we have, say about 20% of the electron goes for the cell synthesis, then say this is complete reaction. Say we are assuming that all the electrons goes for the cell production. So RC minus RD reaction is, you're assuming that all electron is used for cell synthesis. And if we know, say, the fraction of electron that is used for the cell synthesis, we can multiply Fs here. Then the other electron will be used for the energy production. So this Ra minus Rd reaction is the reaction that all electron is used for energy generation. So if we multiply this Fe, then say Fe fraction of electron is used for the energy generation. So the reaction, say, donor plus acceptor would be the product, oxide product plus cell. So this is the overall reaction, and this can be, say, calculated by this. Overall reaction would be Fs times Rc plus Fe times Re minus donor. So we'll practice this in the next slide. Okay, the question here is how can you know this Fs value? So Fs is the fraction of electron donor, so fraction of electron from the donor used for the cell synthesis. So if you have, say, aerobic, say oxygen is as electron acceptor, then the energy production is much higher compared to the case when CO2 is used as electron acceptor. So for a given compound, say glucose, if oxygen is used, then more energy is released from the oxidation reduction reaction, then more cells can be produced. That means Fs will be higher with when oxygen is used as electron acceptor. If CO2 is used as electron acceptor, the energy production is less, so the cell production will be low. So if we compare this, say oxygen is used as electron acceptor and carbohydrates such as glucose is used for the electron donor, then the value would be about 70%. What that means is 70% of electrons is converted into cells and only 30% is used for energy generation. On the other hand, say if carbon dioxide is used as electron acceptor, then only 30% of electron is converted into cell, and the rest of it, about 70% of, say, electron is used for energy generation. So as I told you, sulfate is quite close to the CO2 case, and nitrate is more or less close to the oxygen case. Okay, one more thing. So what is heterotrophic and autotrophic reaction? If you look at this, say the heterotrophic reactions, electron donor is organic material. On the other hand, in the autotrophic reactions, electron donor is inorganic material. So when you classify the microorganisms, heterotrophic reaction or heterotrophs is the microorganism that use organic material as electron donor. The autotrophs is the ones that use inorganic material as electron donor. So which group, heterotrophs or autotrophs, grow faster? There's a simple key for these questions. So if cell itself is C5H7O2, and we usually put the cell formula in this way. This is organic material. So if we synthesize this organic material, say there's a two case. Say if starting material is glucose and carbon dioxide. So which one, glucose or carbon dioxide as a building material, which one requires less energy, glucose or carbon dioxide? So this one and this one, say, is both organic materials. So converting this organic to another organic, it requires less energy. On the other hand, if you, say, want to synthesize the organic cell from carbon dioxide, you need a lot of energy, like photosynthesis. So if you compare the heterotrophs and autotrophs, which one grow faster? It's natural. say heterotrope is usually better than autotrophs. But one thing to consider, so that's the general story. So heterotrophs, they have more cell yield, or the heterotrophs FS value is much greater than autotrophs FS value. That is general. But if you compare, say, this hydrogen, the hydrogen is electron donor and oxygen is electron acceptor, the FS value is 0.24, which is quite close to the heterotropic case. So even though the hydrogen is inorganic material, say, it contains a lot of energy, so the FS value is quite similar to the heterotrophic case. So if you just compare these two, say autotrophs and heterotrophs, say CO2, so we have 2.28, and even hydrogen is used is about 0.04, so there's a big difference. The difference mainly comes from how they make the cell from carbon source. They use the organic material as the building block, and this one they use carbon dioxide as building block. So there's a big difference between the two. And so if you look at this, say, usually autotroph has lower FS value than the heterotrophs. So more or less it's like this. Okay, so that's the general things. And now we're going to jump into the exercises, how to build the overall reactions or balance the reactions. Okay, let's do some exercises for making the full or the balanced reactions. So exercise 6.1 is the reaction methane production from glucose. So what that means is methane production from glucose means electron donor. This is electron donor. And electron acceptor is carbon dioxide, and it combines with electron and make methane. So you can write down the half reactions for the electron donor, and also you can find the half reactions for the electron acceptor, CO2 methane. Then what you need is an FS value and FE value. And FS is given in your textbook, and you can find it in the literature. And also the FE value is just a fraction, as FS plus FE should be 1. So FE equals 1 minus FS, that is 7.72. So what that means is about 72% of electron is used for the energy generation, and only 28% of electrons goes for cell synthesis. And if you write down the cell half reactions, so this is the half reaction of the cell. So to make cell, you need, say, electrons and the carbon dioxide and ammonia. And to make one more cells, you need about 20 electron equivalent when the nitrogen source is ammonia. if you have a different nitrogen source, such as nitrate or nitrite, you will have a little bit slightly different half reactions. I think you'd better, you have it in the half reaction table given in chapter 2. So you're better to practice. So what is how many electrons required for when NO3 nitrate is as electron nitrogen source. So if you write down, say, nitrate and carbon dioxide and C5H7O2N, then in this case the electron required is about 28 electrons, not 20. In this case is about 20. One mole of cell is equivalent to 20 electrons. But if nitrate is a nitrogen source, it's going to be 28. So why more electron is needed? Because you think of it. Say here ammonia, for the ammonia case is 20. So what? There's a big difference. The difference mainly comes from to make this nitrate to ammonia. What's the oxidation number of this nitrogen? It's +5. What about this? -3. So to make +3 nitrogen to -3 nitrogen, you need 8 electrons. That's why you need 28 electrons to make 1 mole cell from nitrate, and you need only 20 electrons when you use ammonia as nitrogen source. I'm sorry. Okay, acceptor is simple. You can write down. Say 8 electron is required to make 1 mole of methane from carbon dioxide. Okay, as for the donors, we use the simplified the carbohydrate CH2O, say like glucose C6H12O6. If you simplify it, say CH2O6, so 6 moles of CH2O, somewhere like this. So anyway, so we can write down the half reaction. So donor minus donor reaction. So this carbohydrate produce electrons, and 72% of electron is used for the electron acceptor to make energy, and 28% of electrons is used for cell synthesis. So the final, say, balanced equation is more like this. So based on this, you can estimate, say, 1,000 grams of glucose produce 12 moles of methane, or in volume, you may say multiply, say, 20 liters per mole. And you also have, say, 1.87 mole of bacteria from 1 kilogram of glucose, or the 211 gram of bacteria. And to make this reaction proceed, you have to add, say, nitrogen, and the nitrogen requirement is about 1.878 moles, or 26 grams of ammonia nitrogen. Okay, I think it's pretty simple. Then we'll do the exercise for the different reactions. Say in this case, this is the aerobic case. So I think this in the aerobic case, the Fs value is just opposite for the compared to the anaerobic methane production case. So Fs is 0.72. So 72% of electrons goes for the cell synthesis, and only 28% of the electron that was released from the glucose is used for energy generation. I think this, say, cell half reaction is the same as before. And what is the electron acceptor for this case? Glucose to methane. This is electron donor. And if all the carbon is oxidized to carbon dioxide, then electron acceptor is O2. Then you may write down the reaction for the oxygen, say 0.28, say times, say so that is the half reaction for the acceptor, and the donor half reaction is the same as before. So if you sum up these three reactions, you will end up with these reactions. So we have to supply oxygen, and also we have to supply nitrogen to make cells. So same mole of nitrogen for the production of cell. So bacterial production is 4.8 mole, which is about, say, 2.6 times compared to that of the anaerobic case. As more cell is produced, 2.6 times cell is produced, nitrogen requirement is also increased by that amount. And also oxygen requirement is calculated as 9.3 moles. Okay, so let's compare the aerobic and the anaerobic processes. So in the anaerobic case, 0.25 CH2O, say, plus 0.014 ammonia equals, say, 0.1 CO2 plus 0.09 CH4 plus 0.14. There's some other minor things, but what's important is here. So if you compare this, I think there is compared, say, nitrogen requirement is much lower as less cell is produced. And the big difference between this aerobic and anaerobic process is the requirement of electron acceptor. So in the aerobic case, you have to add, say, oxygen to it, right? the other hand, say no electron acceptor is required for the anaerobic case. So this is a big difference. In the aerobic case, you have to supply oxygen to the liquid, and actually supplying oxygen to the liquid is not an easy job. Do you remember the DO, so saturation DO of the liquid, so water? See, it's about, say maximum is about, say, 10 milligrams per liter. That means a liter of water may contain only 10 milligrams. So if you say treat, say, a COD of, say, 10,000 milligram per liter COD wastewater, then you have to saturate the liquid for 1,000 times. So it's not that easy job, and in reality, say, a lot of energy is used to supply oxygen in the wastewater treatment plant. For example, say in normal domestic wastewater treatment plant, say with the COD of, say, about 3 to 5 milligrams per liter, the energy consumption is about 0.2 to 0.5 kilowatt hour per cubic meter wastewater, and this is about 50% of the total energy consumption in the wastewater treatment plant. So supplying this oxygen is really a hard job, and it requires a lot of energy. So on the other hand, in the anaerobic process, you don't have to add oxygen to it. So the energy difference is there between the anaerobic and aerobic processes. The other important difference is this methane. So in the anaerobic process, you use less energy because you don't need oxygen requirement. Also, you can produce methane as a valuable product that can be used as an energy source. So in the energy aspect, anaerobic process is much better than the aerobic process, because oxygen requirement is not there, and we produce methane here. So, and also in addition, say this cell is the waste that should be managed, and a lot of, say, the expenses is accompanied by for the management of sludge. So if you have, say, more sludge, if a process produce more sludge, that means you have to spend more money to control or to manage the sludge. So in some, say, anaerobic process, you don't have to add oxygen, and you produce methane, and you have less sludge production. So that's compared to the aerobic case. So if you just compare the two reactions, You may say, I'm going for the anaerobic process because it's more energy-wise and more sludge-wise process. But I think that's not all. So if you think of this sludge production in the reverse way, then it means, say, more sludge production could be better option because it provides the process stability. Say, for a given compound, for electron donor, a process, aerobic process, produce more sludge means they grow fast. That means the process stops very quickly, or the velocity of the process is much faster in the aerobic process. So you can treat the given amount of waste or wastewater much faster in the aerobic process. So if you just compare the process speed or velocity, I think aerobic process is much better. Anaerobic. So this sludge production, say, may be, say, interpreted in two ways. Just for the management of sludge cost or expenses, anaerobic process is much better. But more sludge means better stability of the process. So we must consider two, say, opposite considerations, two opposite facts. So one is good, say, more sludge is in some sense is good, but in some sense is bad. So we must think of those carefully. Okay, let's move to the next slide. Say this is a kind of autotropic reaction, say ammonia conversion into nitrate. So what is? So this is electron donor. So if this is oxidized to nitrate, what's the electron acceptor? That is oxygen. And we can find the number for the Fs or Fe. We need just one of them. So if Fs is 0.1, then Fe could be 0.9. So we use the half reaction for the cell, assuming that ammonia is used for the cell synthesis. And that's natural because there's a lot of ammonia in the liquid. And this is the electron acceptor reaction. And what is electron donor? So the donor is ammonia. So I think you can write down the half reaction for the electron donor. So ammonia to nitrate. So 1 mole of ammonia, it has the oxidation number is -3, and this one has +3. So we know that 1 mole of ammonia will release 6 electrons, or for the production of 1 electron equivalent, you need just 1/6 moles of ammonia. Then, say, you can write down the overall balanced reaction, and there's this. So to oxidize ammonia into nitrate, you need to say pretty much say oxygen, say is more than 1 mole per 1 mole oxygen per ammonia, and so you need a lot of say oxygen. Also, the other thing you should notice in this reaction, say you need oxygen, so pretty much oxygen, and the other thing is pH. So what do you think of pH? If the ammonia is converted into nitrate, what will be the resulting pH? Is going to increase or decrease? Say, if you look at this, say 0.17 molar ammonia produces about 0.33 moles of proton. That is, from that, we can estimate that the pH will drop, right? In addition, say, in this reaction, we have to supply, say, 0.005 moles of bicarbonate. It's not the great amount, but anyway, the bicarbonate is consumed. That means this one is also another factor to decrease pH. So there's two factors that will decrease pH after the reaction, right? But this is the biological reaction, and the most of the bacteria or microorganisms doesn't like the pH drop. So if these, say, nitrifiers proceed these reactions and pH will drop, then they cannot survive. So we have to supply enough alkalinity. To prevent pH drop. So from these reactions, you can calculate what amount of, say, the alkalinity is needed for this. Okay. So this is the example 6.3 is more or less, say, the real fermentation. So it's ethanol production from glucose. So that is quite common in making the liquid or the wines or beers or whatever it is. So wine is making, say, ethanol from, say, grape. So grape is sugar, it's a mono sugar, so it's kind of glucose. So the ethanol production from glucose means what is this one is E donor. And what's the electron acceptor? Electron acceptor is carbon dioxide, and carbon dioxide is converted into ethanol. So we have to know what is electron donor. This one is electron acceptor. And the product is ethanol. So we know how we make the overall balanced reaction. You know what is the half reaction for the cell. You're familiar with this. And what is the acceptor reaction? That is say CO2 to ethanol. So to make 1 mole of ethanol from glucose, from carbon dioxide, you need 12 electrons, or So is it right? Say we can calculate what amount of the electron is needed to make 1 mole of ethanol. So this one has 1 mole of ethanol, say CH3, CH2OH, and oxidation number of this carbon. This is, say, this one is -3, because this carbon and carbon is covalent bond, so you can just break it into this. So CH3, so we have -3 here, and CH2OH, so it's -1, right? So -4. So oxidation number of 2 carbons in ethanol is -4. So you make ethanol from 2 moles of carbon. So the oxidation number is -4, and this one is +4. So we need 2 moles of carbon dioxide. So that is +8. So +8 to -4. So you need how many electrons? 12 electrons, right? So this half reaction is okay. So you can check it. Then the donor is a glucose, right? So glucose release electron, and this electron is used to make ethanol and to make cells. Okay. Then you'll end up with this, say, glucose produced ethanol and cells, and to make cells you need ammonia. So that is kind of the fermentation. Okay, so I think we did 3 examples, say the glucose CO2, or glucose, if this is the aerobic process and this is anaerobic process, where we compare these two and which one is good for the aerobic process and which one is good for the anaerobic process. Aerobic process, the advantage of anaerobic process is energy aspect and sludge. But this sludge may be a negative fact, because so fast sludge growth means stability of the process. Okay, and with the second example is this one, nitrification and or the NO3. So if it oxidize the ammonia to NO3, we need more oxygen, right? But what about the pH? If we produce this or produce this, will there be pH difference? No. I think to complete these reactions, usually it produces 2 moles of protein, and this one also produces 2 moles of protein. So there might be slight differences, but if you say produce nitrate or nitrate, the pH will drop. Okay, and this is the ethanol production. So I think you can do a lot of, say, exercises with this kind of thing. So we need the heterotrophic reactions, and we need autotrophic reactions. Heterotrophic reactions means organic plus, so you may have electron acceptor or not. Or in autotroph, say it's inorganic material, you have the electron acceptors, and you end up you can make the cell reactions. So we can do a lot of things. Can develop the reactions with this principle. It's just a simple. If you know how to make half reactions, so the first thing is what is the donor, and you have to make a half reactions. And what is acceptor? Then acceptor and product. So then you can make half reactions. And the cell half reactions is given, but it changes with the nitrogen source. Usually it's ammonia, but if there's no ammonia, you may use nitrate or nitrite too. And if you know these three, and in addition to this, if you know the Fs values, what amount of the electron goes for the cell synthesis, then you can write the balanced equation for biological processes, biological reactions. So I think that's it for the chapter 6, and you have some homework for the chapter 2 and chapter 6. Chapter 2, you need half reactions, mostly it's half reactions. And chapter 6, you have 3 or 4 problem set to make this balanced equation for different situations. Okay, I think you can do it easily, just following these steps. You find out donor, you find the acceptor, and the final product of the acceptor after accepting electron, and cell half reactions. So I'm gonna wrap up with this third class, and from the next fourth class we're gonna move into the chemical equilibrium, the acid base. Okay, so bye bye. So we'll meet you next time.